Well. Good morning.
So, yesterday we were talking about pointers and arrays, if you remember, and we reached a point in which we introduced the meaning of the second parameter in the main function, which is char star the big square bracket. And so this is a need that actually we can use array to represent string, because as we know, strings are sequence of characters, so we can use array to represent strings. And in particular, if you remember, we already talked about escape sequence concerning with constant strings. The very same escape sequences can be used inside an array of characters. And so into an array of characters is quite important, became much more important the string terminator, because of course you may have a string which is much larger than the string you will end up printing the standard output, due to the fact that once you reach the string terminator, the printf function doesn't write any more character from then on. Okay, so this is it. So let's have a look at this piece of code. This program is almost quite straightforward once we have understood the notion of array. In particular, in the very first line, just after the signature of the function main, we have a declaration for an array of characters. As you can see here, we are not stating how large is the array, but we can guess it because of the next assignment. And by the way, this operation can be done just during the declaration of the array itself. So you can initialize the array by using this syntax, and you cannot use it later on. So if you try to assign a full array by using that syntax, you end up in an error. But we will see. So this syntax basically tells the compiler we want to create an array of characters whose length is the length of the full string, including what it comes before the string terminator. So the here word, let's say, and every single symbol inside the word is considered as a character. Okay, so the escape sequence, for instance, \n is a character. The escape sequence \b is a character, and so on and so forward. The string terminator is a character. The space is a character, and so on and so forward. And the array has length equivalent to the length of the string plus 1, because at the end of the string we have to consider the string terminator, which is implicit in the fact that we are declaring, let's say, a string. Now, if we try to print the full string, something wrong happened here. No, okay, it's correct. If you try to print the full string and the character in position number 3 into the array, well, position 4 actually, but index it by 3, you end up in what you can see on the bottom of the slide. You should see at the bottom of the slide, actually, because for sure you are not able, at least on class, to see it. Okay. So let's try to understand what's going on here. Well, the first thing to be printed in the standard output is quotation mark 8 quotation mark space. Okay, and so that's the first line of output is quotation mark 8 quotation mark, and of course the space is not visible. Then we have a new line. So this new line brings us to the new line, to the next line in the standard output. Then we have a space which should be visible because of the fact we are printing something after the space. But after the space, so the space is the symbol coming just after \n. We have another escape sequence, which is \b, which means backspace. So by issuing that character, we are deleting the previous character. Okay, so by using the \b, we are deleting the space coming just before \b, and that's why on the standard output you cannot see it, because it is printed, but just after printing it, it is immediately deleted. It was immediately deleted, and then we have again we print en. So just after the \b, we print on the standard output en, and then we print I. But that I is not present on the standard output because, again, the next character is a \b, which is backspace, and then the character I is deleted by the \b. And so after en, we print d and s. So the full word is ends, and that's why on the standard output we have ends, space, and you can see the space, and okay, on the standard output, for some reason we have quotation mark that shouldn't be there, but probably this is due to show you that we have, I place it there to show you that we have a space just ends, just after ends, and the word here is not present, and this is due to the fact that we have the string terminator just after the space. Okay, so the string here is not printed because of the string terminator. That's it. Oh, no, okay. Now I understood why there is the quotation mark. This is due to the fact that the string ends with the space just after the ends word, and we don't print here, but on the printf call we are also printing the fourth character in the string, which is of course a quotation mark, and that's why on the standard output we can see the quotation mark. Okay, so if you have a look at the third line just after the signature of the function main, you can see that the last parameter of the printf function is the fourth character in the array a_string, which by the case is of course a quotation mark. Okay, is it clear? Any question about this stuff? Okay, so now we are able to deal with strings. So strings in C basically are arrays, sequence of characters. But of course it's, it could be useful to have some kind of function to deal with strings too. So if you want to cut two strings, how can we do it? If we want to compare two strings, well, of course we may try to write a function to perform this operation, but luckily the standard C programming language provides us some function to deal with strings for free. Okay, so we don't have to implement them, they are provided by standard libraries. So the one we discussed in the POSIX system. So let me mention some of them. The first one, well, first of all, to use all these functions, you are required to include the header strings .h. So if you try to use them and compile a program without including the strings, string.h header, you end up in an error, well, in a warning saying you are using function which has not been declared before using them. So the first useful function to deal with strings is string cut, which basically join two strings. And the idea is that you have a string S1, so an array or a sequence of characters pointed by the pointer S1, and an array of characters or a sequence of characters pointed by the pointer S2. And you, by calling this function, you end up in the merge, the union, the juxtaposition of the two strings in something pointed by the pointer S1. Okay, so the result of joining these two functions is contained by the pointer S1. And of course, you get also the result as a pointer to the memory location in which you have the two strings joined, the two joint strings. Then we have a function to compare two strings. And again, the two strings are compared up to the string terminator point. Okay, and the string compare function return an integer that would be an integer value that would be smaller than 0 if S1 is lexicographically smaller than S2, so comes before in a possible dictionary, let's say. Greater than 0 if greater than 0 if S1 is greater than S2 in the lexicographical order, and equal to 0 if they are exactly the same string, again up to the string terminator. Okay, so it could be the case if you have two array of characters that are not equal, because something is different after a string terminator, okay? But the string compare function still returns 0, because up to the string terminator they are totally equivalent. And this is the point. Other two useful functions are the string copy function, which is meant to copy again, a string to another, well, the content of an array of character into an array of character up to the string terminator, again, okay? And this is it. Again, here we have a source, which is the second parameter, and destination, which is the first one. Oh, by the way, probably I missed to tell you what's const. Well, const is a reserved word which is meant to say, look, I'm not going to change this parameter inside the function. So the function is not going to change the content of the parameter. Okay? So as you can see here, we are saying that we are not going to change the source string, but for sure something may occur on the destination string. And in this particular case, for sure, we are changing the destination string, because we are copying everything from the source into the destination array, or better, the destination, the memory pointed by the destination parameter. Okay. Again, also in this case, we are returning the memory location corresponding to the destination. And finally, we have another function called string length, which, of course, basically count the number of character, or visible character in the string, and return a value, which is the number of bytes required to represent the full string. Okay. So if you remember the character type was the character taking one single byte. So the string length function returns number of bytes required to represent the full string, and number of bytes required to represent the full string. And the return type is size t, which is a standard type used to represent the number of bits used to required to represent a data structure. This is it. So let's have a look at some piece of code using this function. For instance, let's assume to have 3 different arrays. As you can see, the arrays, may be much larger than the string we want to deal with. It's not really important. Important they are at least large enough to contain the string we want to deal with. The first 2 arrays are initialized by the 2 strings let me see and how it works, while the third array is not initialized at all. So if you remember, we said that the arrays in the C programming language are not initialized, so at the very beginning of the computation it contains random values. Okay? By default, by the ANSI standard. It could be if you are using some specific compiler or some specific operating system that actually the array is initialized. But in the standard ANSI C, you don't know. Now, by using the string copy, so let's have a look at the 4th line of this code. The fourth line of this code is basically copying the content of the array A string into up to the string terminator, which is implicit on the fact we are using quotation mark. So just after let me see space, we have a string terminator, an implicit string terminator due to the fact we are specifying the string by using the quotation mark. And so, up to the string terminator, we are copying the content of the A string array into the C string array. Okay? So we are copying the string, basically. Is it clear? Yeah?
So when we create the array with string characters, we've got, for instance, A string, you've got let me see, and then what follows, is it empty or random characters?
Can you repeat your question? Because
so when we created this string vector, string array, we've got the first part, so this array is formed by 100 elements.
Yeah.
So the first elements are going to be let me see.
I see your point. No. So, by declaring an array of character whose length is 100, I'm saying that the length of the maximum length of the string I'm dealing with is 100. So 100 is the number of characters in the string, not the number of string I'm dealing with.
Okay, so
so the first, just to clarify the point, the first value, let's say, the first value in the array A underscore string is the capital letter L. Okay?
But then after the last phase, what do we have? It's empty. Or do we have random characters?
Well, after the last phase in the string, let me see. We have a string terminator, so \0.
Okay.
And then after that, random values.
Okay.
Okay?
So then when we copy the A string into C string, so the first part is going to be identical, it's going to be let me see, but then the second part is going to change.
The second part might be different.
Okay.
So it could be the case that, for instance, let me count the number of characters in the two strings. So the first string has 7 characters plus the string terminator. Am I right? No. So 7 plus 4, 11, 12 characters, including the string terminator, while the second string has 4, 7, 5, 13, including the string terminator. So if I try to copy the first string, so if I copy the content of the A string into the B string, okay, I'm not changing the very last implicit character, which is the string terminator in B. So the A string at the third position may contain, I don't know, 3, for instance. Okay, that 3 is not copied upon on the B string. Okay. So this function is useful exclusively for the string. If you want to copy something different, for instance, if you want to copy the content of an array to an array of integer into an array of another array of integer, you have to use a different function. Because I mean, what we interpret as a character are actually numbers. So the \0 is a number, okay? And so if you are trying to copy an array of integer and you discover that number, you end up in copy, so you stop the copy. And so that's why this function is not useful to copy an array of numbers, for instance, but it's specific for arrays of strings. So once I've copied the array, the content of the array A string into the array A, once I've copied the string contained by the array A string into C string, I can print the content of the string by using, again, the %s notation. So S stands for string, of course, and so by doing this operation, you end up exactly where you expect to be. Okay. And what by using string cut? Well, string cut again is a function that is meant to copy attach to the first string the content of the second string. Okay, up to the string terminator, of course. So it replaces basically everything after the string. Well, it replaces everything after the second last character in the first string with the content of the second string. Okay, why second last character? Because the last character of the first string is of course the string terminator. Okay, and the result in this case is again what is assumed to be. So if we want to simulate, let's say, what's going on here, by performing the first operator, we are assigning to the so by performing the string cut function, by calling the first string cut function, we are basically appending at the end of the let me see string, the string how it works. So the string represented by the C string array is now let me see how it works. Okay? And so see, if I try to execute the next instruction, I end up in cut is cut let me see how it works. Now, as you should see, actually, the next instruction is a printf function in which basically we are comparing a string, b string, a string, and a string, and b string, a string. And this is just a way to show you that these functions are meant to compare strings. And as I told you, the comparison is based on the lexicographical order of the strings. Of course, you may ask whether the capital letter comes before or after standard letter. Well, this depends on the ASCII encoding, okay? So it's a kind of extension of lexicographical order, because of course here we can deal also with non-alphabetic characters. Oh, by the way, the function string compare, as I already told you, the function string compare, which is the second one, return an integer to say whether the first parameter is smaller, greater, or equal than the second one. This is quite standard. So usually the comparison functions in the C programming language and the C++ programming language use this convention. So instead of returning a true or false, comparison function returns an integer value whose negative result corresponds to, say, the first parameter is smaller than the second one, 0 corresponds to the fact that first parameter is equal to the second one, and return value greater than 0 corresponds to the fact that the first parameter is greater than the second one. Okay, this is quite standard. So every time you will be required to produce a comparison function, the convention is this one. Would be this one. And you cannot see it because of the desk, of course, but of course you can also use the string length function to get the length of a string. Again, the string length function is not the length of the array containing the string. It is the length of the string up to the string terminator. This is it. Any question about this stuff? No question. Done. Great. Okay. So, by the way, you at home, can you send an acknowledgement just to tell me that you are still alive and we can go on? In the meanwhile, I'm moving to the next slide. Okay, so what are we going to see next? In the next unit, let's say, we will see streams, dynamic memory handling, and we will see how to define new data structures. So we will see what it is, all this stuff later on. Everything is okay. Okay, great. Okay. So, let's start immediately. So, we already discussed about what is a file descriptor in the in POSIX system. If you remember, we mentioned that file descriptor are numbers meant to describe a file from the operating system point of view. There are three main, the three most important file descriptors are actually 0, 1, and 2, which corresponds to the standard input, standard output, and standard error. Okay? Now, we already mentioned it. So how can we handle files and in general standard input and standard output from the point of view of the C programming language? We can do it by using what is called streams. So what is a stream? A stream is a logical object, a logical interface meant to read and to write to read from and to write to files. Okay? Why logical? Because actually there may be Since in POSIX every single device is organized, is handled by using files. For instance, keyboard is a file from the point of view of operating system, and so on and so forward. Actually, it may be the case that you can read exclusively one character per time. But of course, if you want to read a file, you are not interested in reading the file one character per time. You may want to read a full line, for instance, from the file. So to do it, you need, in some sense, a folder level from the file up to your, in the middle of the operating system and your program. And this layer is what is provided by using streams. Okay? So, before using a stream, which may be a file, or again, as I told you, a keyboard, a webcam, and so whatever you want, for sure you need to open it. So, how can we open a file? Well, to open the file, we can use the function provided by the SStudio IO interface, which is fopen. So the fopen function is meant to open a file descriptor. So how can we provide the name of the file we want to open? Okay. Well, the first parameter specifies the name of the file we want to open. So if we are dealing with a program which want to open a file in the current directory and the file is named people.txt, in that case we may pass as parameter the string quotation mark people.txt quotation mark. And that's all. Okay. What about the second parameter? Well, when you open a file, you may open the file to read it, to write it, to create it, to append data to the file, or to recreate from the scratch. Okay? And all these modality to open the file are different. So the API, so the advanced programming interface, require you to provide the modality in which you want to open the file. So if you want to open the file exclusively from the reading point of view, so if you exclusively want to read the file and you don't want to change the content of the file, you may provide the strings quotation mark or quotation mark as second parameter for the fopen function. In that way, you are saying, look, I want to open the file, but exclusively from the reading point of view. So my intent is to read the file and not to write it. Okay? If you want to write the file from the scratch, you will open it by using the W modality. If you want to do both of them, you will use R+, the R+ modality. Okay? There are many more modalities, but I don't want to discuss about them in details. For instance, you can open a file and attach data at the end, and so on and so forward. You may have a look at the main page of the fopen function. By the way, of course, as already told, once you have installed everything concerning the compilation and so on and so forward, you have also installed the main pages concerning the C programming language. So if you search man fopen, you end up in the manual of this specific function. Okay. Of course, once I have opened a file, oh, by the way, the function fopen returns a pointer to a file, data structure, which is meant to store this, how can I say, a descriptor for the stream you want to deal with. Okay. And of course, once you have opened a stream, you may want to close it. Why? Because the stream is a layer in between of the real file and your program. So it may be the case that you ask to your program to write something in the file, but it hasn't been done yet. Okay, to improve the efficiency of the overall efficiency of the system, it may be the case that what you already written from your program point of view is not really written from the file point of view. So to perform all the operation that hasn't been accomplished yet, you have to close the file. And in that case, all your requests will be fulfilled immediately. Okay. So to close a file, you have to provide as parameter a variable containing the descriptor of the file which has been already opened by the fopen function. Okay. So once you call the fopen function, you get a value which should be stored inside a variable of the type pointer to file. To close that file, you have to provide the very same variable to a fclose function. And the result of the fclose function is an integer value, which, as you may imagine, is an error code. So if the fclose function returns a 0, means everything went in the proper way. If the fclose function returns something different from 0, means that there was an error. Okay, and this is it. So something more about the file handling from the C programming language. Here, for instance, by using fget C, we are saying that we want to get the next character of the file. So all the files are read by a character actually from the C programming language point of view. So you may ask the next character because they are sequentially read. Okay, and the result will be an integer value. Why an integer value? Well, an integer value because actually a character is a value. If you remember, by using character, we may also get, by using character, we may also represent all the values going from 0 up to 2 to the power of 8 minus 1. Okay? So, to avoid to mess up things in a nasty way, let's say, and to allow specific implementation of the C programming language to handle the errors, this function returns an integer value. Why? If you are getting a value which is greater than 2 to the power of 8 minus 1, then there was an error. Okay? So it's a way to allow to admit errors in the output of fget C function. Of course, you can, if you open the file in the writing modality, you can also write a file character in the file, and this is done by using the fputC function. As you can see, the first parameter is the character we want to write, or better, the value we want to write into the character. The second parameter is the file we want to into which we want to write our character. Of course, I mean, it's not really easy to write data and read data in this way. Just imagine a situation in which you want to read, I don't know, a number. And of course, a number consists in many different digits, may consist in many different digits, and so if you read the file one character per time, you end up in requiring a function to read the full number. So so that's why actually we have a high-level set of function to handle streams, and in particular we have fscanf and fprintf, which are totally equivalent to the scanf and the printf function we already seen, with the difference that the printf and scanf function print and scan from the standard output to the standard output and from the standard input respectively, while in this case we are printing and scanning from a file. Okay? Again, since everything in a POSIX system is handled as a file, also the standard input and the standard outputs are files, are handled as files. So in this case, you can provide the standard input and standard output as files to this function and emulate the behavior of scanf and printf. Okay. So for these two functions, as the first parameter, we have, of course, the file descriptors we want to deal with. And everything is exactly the same. So as I just said before, printf and scanf can be emulated by using standard input, standard output, and standard error. Okay? So if you want to use fscanf to scanf, let's say, you have to use the, let's say, reserved variable standard in, std in, which is a standard variable meant to represent the standard input. For printf, you have the standard output or standard error. Okay? This specific file descriptor should not be open or closed. They are open and closed by default. Any question? Is it clear? Not really. What about you? More or less. What is not clear?
The last part.
The last part. So, have you understood the meaning of fscanf and?
If you can repeat it, it's
Okay. So, can you remember the meaning of scanf and printf? More or less. Yeah. Yeah, exactly. So fscanf and fprintf are the file version of the very same function we saw for the standard input, the standard output. Okay. So by issuing fscanf, you are basically issuing a scanf call, but not on the standard input, but on a specific file. So you are reading either a character, a decimal number, or a 40-point number, but on a file. Okay, and the very same holds for fprintf. So in that case, you are not printing on the standard output, but you are printing in a file. Now, since the C programming language is providing three, let's say, special variables, which are sdin, sdout, and sdir, which are meant to represent the standard input, the standard output, and the standard error respectively, you can emulate the behavior of scanf and printf by using fscanf and fprintf. So by issuing scanf standard input, so quotation mark, percentage d, comma, ampersand a, I'm basically reading from the standard input a decimal number, and this decimal number is placed into the variable a. Okay? Okay. And while the second line is meant to print into the standard output the string we can emulate printf. Okay? Notice exactly the very same syntax can be also used to read and write data from and to files. Okay, with the only exception that instead of placing standard in and standard output and standard error, you need to place the file descriptor you have open and you are going to close. That's it. Okay, one thing I missed to say, and I'm saying in this slide, is that actually there are two quite similar functions also for for arrays, which allows you to read data from arrays and write data to arrays. Okay? So a buffer is basically a location in the memory meant to store data, let's say. If you want to read data from a string which is stored in memory, either into array or somewhere else, or if you want to write a string in an array, so into memory, you may use scanf and sprintf. So these two functions are meant to read formatted data from memory and write formatted data into the memory. Okay, so let's have a look at this piece of code. We have an array of characters whose length is 100. So we can store any possible string containing at most 99 string characters plus the string terminator. Okay. So by issuing the first command, we are reading a decimal number from the second word in the command line. So the command line, once we compile this program, we can execute it. Okay, and in executing it, we issue to execute it. We need to issue a command in the command line. This command in the command line may provide not only the name of the program itself, but also some parameters. If you remember, argv is the second, well, you can see here, is the second parameter of the main function. So it's meant to store all the words in the command line, including the parameters. Okay? The first word in the command line is the name of the program we are executing. The second word in the command line will be the first parameter of the program to be executed, and so on and so forward. Okay? So by issuing the scanf call, we are basically reading the first parameter of the command line used to execute the program. Okay, that parameter may contain, I don't know, everything you want. Okay, a character, a number, or whatever you want, basically. But here we are assuming that the first parameter is actually a decimal number. Why can I say it? Because the second parameter of the scanf function call is the formatted text decimal number, and you can see it because of the percentage d notation. So by writing percentage d, I'm saying that I'm trying to read a decimal number, okay? And the decimal number should be placed into the variable a. This is the third parameter. But this decimal number should be read by on the first argument, the first parameter, so the second argument of the command line. Okay. So in this way, I'm in some sense interpreting a string, because at the command line we are writing a sequence of symbols, and this sequence of symbols can be a sequence of digits, a sequence of letters, as any possible things, and that's why all the parameters and the command lines are dealt with as strings, because we don't know the meaning of that data. And by issuing scanf, I'm basically interpreting the first parameter of the command line as a natural number. And now the variable a is a value, no more a string. Okay? Is it clear? So while argv1 is a string, a is now a value, and will contain the interpretation as a decimal number of the string passed as first parameter for our execution. Okay, Now, once I've read the content of the first parameter, in the command line, I can print the string. The first argument was, and the value of the first argument from the decimal, interpreting it as a decimal number. This string can be written into what? Into the buffer. So into the array of character I've just declared. Okay? So I'm not printing that string into a file or into the standard output. I'm printing it into a buffer, into an array. Is it clear? Can you follow me? What about you? Okay. What's your name, by the way? Yeah. Okay.
Excuse me.
Yes.
A is an integer.
Pardon?
A is an integer.
Yeah, right.
But buffer is a character.
Yeah, an array of characters.
So when I print with sprintf A in buffer, it returns to be character.
Yeah, so just try to remember what's going on when we try to print by using printf instead of sprintf. So we are trying to print some data in a formatted way. So we have a text and all the data coming as second parameter, third parameter, so from the second parameter on is turned into a string. And this is basically what occurs here. So the third parameter of the sprintf function is an integer value, but this integer value is inserted into the %d placeholder, let's say, into the string. So by doing this operation, this value is turned into a string again. So, but instead of doing this operation into the standard output, you are doing this operation into the buffer. Okay. So after the sprintf function, you may use all the functions we saw at the beginning of the lesson. So string cut, string copy, string compare on the buffer. Okay. Okay. So, okay, so now we understood more or less what's going on with files and so on and so forth. And let's move on. And let's take a quite simple exercise to be performed by using the C programming language. So, our aim is to write a function that takes a natural number as parameter and returns the first n prime numbers. Okay? So we want to compute the first n prime numbers, where n is a parameter of the function. Any problem in doing it? Are you able to do it? What about you at home? Well, yeah. How can we return a set of prime numbers? Is there any way to return a set of prime numbers? Till now we saw functions which are able of returning integer value, one single integer value, character, one single character. We saw the signature of function dealing with files, which are returning pointers, but we never saw any way to return a set or a sequence of prime numbers. Do you agree?
Can we just transform the prime numbers into strings?
So returning a single strings. Have you ever seen a function returning a strings? A string? No. Okay. So again, one of your colleagues was suggesting that we may return a string instead of returning a sequence of string and then turn back the string into the sequence. But actually, there's no chance to return a string from what you saw until now. Okay. So how can we do it? Well, it would be useful. It would be nice to use array, but we have some problems in using array to return the sequence of first and natural number, of first and prime numbers. The first problem is that the size of the array is not known at completion time, so we are not able to declare the array at completion time. Okay. If you remember, when we when we discussed about the array, we saw that to declare an array, you must provide the size of the array. And the size must be a constant number. So it's not possible to declare an array saying, I want the array to contain n values, where you don't know the meaning, the value of n at completion time. Moreover, even if this would be possible, even if this was possible, the array is declared, would be declared inside the function. And we need to return it outside the function. This is not possible. Okay, because an array is a sequence of a memory location. Okay, if you declare the array inside the function, once you exit the function, the declaration of the array doesn't hold anymore. Okay. So it's not possible to use the array. A naive solution would be to overestimate the value n passed to the function and pass the array as a parameter. So in doing this, we basically need to pass as first parameter of our function a pointer to the array, which will contain the first n prime numbers. Okay? Can you follow me? So in this way, basically, inside the function, I'm able to, inside the function get primes, I'm able to change the content of the output array. And for instance, I can do it by the last two lines. So the first line, I'm declaring the output array, and in the last line, I'm basically calling the function, which is able to compute the first n prime number. But I mean, also this solution has some drawbacks. In particular, if the n is quite smaller than the constant number of the size of the array I just declared it there, I'm wasting space, because many of the cells of the output array wouldn't be used at any time. Okay. If otherwise the number n is greater than 100,000, I'm basically performing a nasty operation, because I'm using a memory location which is not reserved to store primes number. So, and moreover, I'm not able to understand what's going on. What's the meaning I mean, if you read the code, you miss the first, reading the code for the first time, you may miss the meaning of the first parameter. So it's not clear what's going on here. So how can we solve the problem? Well, to solve the problem, we may need a kind of mechanism to allocate, to reserve the right amount of memory at runtime. So in some sense, we need a way to say, okay, at runtime, okay, I want an array having exactly this space. We need a mechanism also to free this space, because as soon as the result is not more needed, we may need to, we may want to free this space and get back the free space for our program. And we may also want something to resize the allocate memory, because if you keep repeating asking this question many times, the space required to store the first n numbers may be resized to store the next n numbers. Okay? So how can we do it? Well, first of all, we have to notice that pointer can be used as a kind of a reference to this memory which we reserve for our goals and which will be free. And this can be done by using what is called dynamic memory handling. So dynamic memory handling is a mechanism to reserve a given amount of space at execution time. Okay. So you when you're writing the program, you don't know how many prime numbers you want to compute, because this can be done given at execution time. For instance, by issuing a command whose second parameter is the number of prime number you want to compute. So we need a way to say, okay, I want, since at the execution time, my second parameter tell me that I need to compute the first 100 prime number, I need an array having 100 prime numbers. Is it clear why can we cannot use to achieve this goal the arrays? Is it clear? No. Is it clear? Yes. Is it clear? More or less. Can you repeat why we cannot use array to solve this problem? Yeah.
Because we don't know the size we need as the completed time, so we have to do this mechanism.
Okay, yeah, more or less. So the idea is that by using the arrays, we need to know the exact size at completion time. So either we decide to reserve more space than needed, and this can end up being a waste of space, or there's no way to estimate at completion time the amount required at execution time, and that's why we need dynamic memory handling. So how can we achieve this dynamic memory handling? We achieve it by using some functions provided by the standard C programming language, which allows us to allocate and deallocate the memory. Okay? And these functions are provided by the stdlib header. In particular, we have a malloc function, which is meant to allocate uninitialized memory. So we call malloc saying how many bytes of space, how many space in bytes we are requiring. And this function returns a pointer to a memory region containing memory region whose size is exactly the number of bytes we are requiring. Okay. So if we want, for instance, let's assume we want an array of integer having size 100, so having 100 cells. So we want an array being able to store 100 integers. We have to provide to the malloc function 100 multiplied by the space of one single cell. Okay, required by one single cell. So an integer requires 4 bytes, so we have to pass to the malloc function 100 multiplied 4. Okay. And this code will return you exactly 400, a pointer to 400, a pointer to a memory, allocated memory whose size is exactly 400 bytes. Now, what if you need what if you want to allocate an array of values? Well, to allocate an array of values, you can also call the calc function. The calc function works more or less like the malloc function, with the difference that after allocating the space, you are getting also initialized, so the space is also initialized to 0. And the idea is that in this specific case, you are passing to the function the number of elements you want in an array and the size of each element in the array, and you end up with the exact space allocated. So why malloc is needed if you have the calloc function? Well, it may be the case you want to allocate space for something different from an array, and we will see. So let's assume you want to allocate the space for a floating point variable. Okay. This is just an example, but we will see later on that the malloc function is also useful in many different cases. So the third function that can be used to deal with the dynamic memory handling is the realloc function, which basically takes a pointer to a memory location which has been allocated before, and resize it. So resize the allocated space up to second parameter number of bytes. So this is a kind of shortcut to what? To allocate new space corresponding to byte size and copying what was present in the first memory allocation, what was present in the memory pointed by mem pointer into the new location. So at the same size, you are allocating new space and copying. You don't lose the content of the previous memory allocation. Well, of course, after copying the original memory, the original space is deleted. Okay. And finally, so what if you keep allocating space and never release it? You end up in wasting a lot of space. Because it may be the case that, for instance, some of the space you already allocated is not more useful for your program. So you have to deal with all this allocation, and this is done by the free function. So the free function basically takes a pointer to a memory region, and the reserve. So if the malloc function reserves the space, the free function free it. So that particular space location is not more available for your program, but return to be available to everyone who needs it. Okay. So here you can see a quite strange usage of the void type. If you remember, the void type is meant, well, we introduced this as a type meant to say, look, my function is not returning anything. Okay? In this case, we are dealing with a pointer to void. So what's the meaning of pointer to void? Since at this level you are not saying for which data type you are using the memory, the functions are not providing any specific data type for it. So by using void asterisk, you are saying that this is a pointer to memory, which can be used for any kind of data type. Okay, so it's a kind of way to say you can do it anything you want on this memory. Okay. Now let's have a look to our exercise and try to understand what's going on. So by using dynamic memory handling, we are now able to write a function which takes as parameter a number, which is the number of prime numbers we want to get, and returns a pointer to the memory location which is allocated inside the function. So the function is taking a number, allocate the space corresponding to that number, and returning a pointer to that memory location. Okay? So inside the function, so this is the signature, and it's more or less easy to understand what's going on. Here we are taking a number as parameter, and we are returning a pointer to a memory location. And the memory location is a memory location reserved to represent a sequence of unsigned integers. Okay? Is it clear? Great. So the first thing to do here, we are missing a semicolon. However, the first thing to do is to, in the second line, declare a variable. As I already said, here we are missing a semicolon just after the instruction. And the next instruction is an assignment. And this is the tougher part, let's say, of this piece of code. Here, I'm assigning to the pointer p, to the variable p, what I'm assigning? I'm assigning, well, so let's have a look at the, let's see, what is included inside the parenthesis. What is included inside the parenthesis is a typecast. So I'm taking something and I'm turning it into something of different type. Okay? Here I'm saying I want to assign to P something that should be interpreted as a pointer to unsigned integer. Okay? But now let's have a look to what is just after the typecast. So just after the typecast we have a calloc call. So the calloc function is a function meant to reserve the space for a given amount, for an array of given number of cells. In particular, the first parameter of the calloc function is the number of cells of the array we want to reserve. Okay? So here we are calling the calloc function, say we want to allocate the space for an array having n cells. Okay, so the first parameter is meant to say I want n cells. What about the second parameter? Well, the second parameter of the calloc function, if you remember, was meant to tell calloc the size of each cell in the array. So the second parameter of calloc is meant to tell the size of each cell in the array. Now, how can I get the size of unsigned integer? We know that in my system is 4, but we also know that in that the standard C programming language is providing a lower bound for the number of bytes for each standard data type. But that's a lower bound. So it could be the case that in some system unsigned integer takes 8 bytes instead of 4. Okay? So how can I decide how many bytes are required to represent an unsigned integer into the system in which I'm compiling my program? This can be done by using the function sizeOf. So the function sizeOf takes any type, so the standard one and the one we are going to define into our program, and evaluate the number of bytes required to represent that specific type. So by issuing the the call size of unsigned int, I'm getting the number of bytes required to represent an unassigned integer into the compilation system. So into the system in which I'm compiling my program. Okay? So the calloc function takes as first parameter the number of cells we want in our array. As second parameter, the size of each cell, and returns a pointer to a memory location which is able to store an unsigned integer. Okay? Remember, the calloc function returns a pointer whose type is void star. Okay? So, since we want to deal with integer values and not void values, we need somehow to tell our program that we want to deal with integer values. And to do it, we use the typecast. Okay, so the typecast is meant to tell our program that the memory location that we have just allocated is not meant for general use, it is used to deal with integer values, unsigned integer values. Any question? Not really? I mean, the first time I saw this syntax, I was a little bit concerned because actually, here I'm specifying twice the type I want to deal with. In particular, I specified once when I call in the size of, and I specified the second time in the typecast. Okay, so in some sense, this is a redundant way of allocating memory, but this is the syntax of the C programming language. Okay. Now, once we have performed this operation, P is a pointer to a memory location which is able to store an unsigned integer values. And since we saw that pointers can be used just like arrays, so the syntax of the arrays can be used into pointers or handling pointers, we can basically fill the array we have just allocated in a very standard way, as we may have done in a main function, let's say, and then return the pointer P.
So in the main, we just define the array with argument P.
No, in the main file, we don't need to define any array. We need to declare a pointer, just like we did it in the second line, and assign that pointer to the value returned by the getPrime function. Okay? Let me see whether the next line explains what I told you. So this is a call to the getPrime function we have just implemented. Here, I'm calling the getPrime function, trying to compute the first 1000 prime numbers. The result will be a pointer to a memory location which is able to store 1000 unsigned integer. Okay, so this is it. In this way, that pointer is a pointer to the result of our computation. Now, how can we handle the number? So how can we read the number? How can we see what's inside the result? Well, we can use the standard array notation, as you can see at the fourth line. Okay, so in the first line we are declaring a pointer to a memory location meant to store unsigned integer. We are calling the getPrime function. The second line is basically a for loop which iterates over all the results. The third line is a printf, and on the third line you see that the last parameter is a seems to be an array, or better, seems to be a reference to a cell in an array. Actually, primes is not an array, is a pointer. But as we already saw, arrays and pointers can be used from the syntactic point of view exactly in the same way. Well, there is one single difference. You cannot reassign an array, but you can reassign pointers. Okay? So, in using this notation, using the syntax you can see on the fourth line, we are basically saying, I want to know the content of the output of the getPrime calls in position I. I think Fortran has some, well, probably, I mean, Fortran 77 for sure doesn't have dynamic memory handling. Well, I'm not sure about it actually, but I think to remember that it does not have dynamic memory handling.
I use this, but it's quite different. We use the command allocatable, so we don't specify. We specify the dimension
Of the array.
Matrix,
yeah, but this is done. This is done because on the I mean 77 version of the Fortran programming language, you don't have. I think to remember, you don't have dynamic memory handling. So you are required to specify a constant size for the data structure you have to handle. So, but I mean, this is a way to this is simply, long story short, this is simply a way to specify dynamic size for the array you want to deal with. Unfortunately, you have to remember to free the space. So once you have done everything you need to do, you have to call the free function on the memory space you have allocated. So that the memory space go back, I mean, to the system, and the system handle it as it would. Okay, this is, I mean, this is a major issue in the system. I mean, this is a great feature in the C programming language, but it is also a major issue in the C programming language, because most of the mess with programming comes from the manual dynamic memory handling. If you came from Python, for instance, you have anything like this. So in Python, you want to deal with an array having size n, you simply start using the array of size n, that's all.
Then the thing that I don't understand is that the first line, from what I can understand, we already know that we want the first 1,000 numbers.
Mm-hmm.
And what if I want to decide it?
Okay, but this is an example. Okay, you are arguing that from the first line we already know the size of the output. Yes, this is true, but actually, just imagine a situation in which we wrote the getPrime function and we included it into a library, I don't know, 1 year ago, and then this piece of code has been written, I don't know, 10 minutes ago. Okay.
Yes, okay. I
so that piece of code, the piece of code so the function getPrimes is totally general.
I explain myself in a wrong way. For example, in Fortran, I define my variable.
Mm-hmm.
I put the command allocatable, so I don't have to decide the dimension of the array when I define it. But for example, I define another integer, which I call n, and then I give as an input n, and then I allocate the array.
So let me mesh up this piece of code and one piece of code we see half an hour ago. So the piece of code we see half an hour ago was a scanf function which takes the first parameter from the command line and turns it into an integer value. So it was scanf. Let me go back just to. Oh, here we are. So with the third line in this piece of code, I'm basically reading the second parameter of the command line and I'm turning it into a value, which will be stored into the variable a. Okay. Now that variable can be passed as actual parameter. And can be passed, so the variable a can be passed as actual parameter to the get prime call. So in that way, I'm basically writing a program which takes the first parameter of the command line, turn it into a decimal number, and compute all the first and not one a number, not one prime numbers. Okay, so it is possible. So. Okay. Okay, let me go on for another. No, let's have a break. Okay. Okay. So let's start again. So some of your colleague online is asking whether the cast on the third line is really necessary. Okay, so the typecast on the third line is the one in which by which we are turning a pointer to void to a pointer to unsigned integer. Okay, and they asking whether it's really needed, but actually no. I mean, there could be an implicit typecast, but it really depends on the compiler you're dealing with. And moreover, I mean, by doing that operation, you are in some sense strengthening so you are in some sense tightening your code to that specific data type. So in doing so, there are less chances to commit any error. Okay. So let's assume, for instance, you have many pointers. And of course, you are not writing one single function at a time, but you may end up writing thousands of functions in one single project. So it could be the case that you usually use P to represent pointer of integer or assign integer, but for some reason in that specific function, P is I don't know, something different because the function was meant to represent a different function than with respect to the usual function you are implementing. So if you use this typecast, you get an error, or better, a warning from the compiler saying, look, you are trying to assign a pointer to unsigned integer to something which is not a pointer to assigned integer. While if you leave if you don't use the typecast, you may end up doing something wrong and you are not getting any error. So in some sense, using the typecast let you to give you the chance to better control your code. You are enforcing, in some sense, the static checking of the compiler. This is it. So let's move to a different exercise. So we understood that dynamic memory handling can be used to reserve space for arrays. Okay. But now let's focus on a different exercise. Let's focus on the exercise to represent a set of students instead of a set of numbers. And you know that each of these students have a name, a family, well, a first name, a family name, an ID, and of course you have each student has a set of courses and marks. Okay. So how can we represent this kind of data structure? Okay. So how can we represent this situation into our programs? Well, a possible way to represent it is to have n strings, so an array having n strings to represent the names of each student, an array of n strings to represent the family name of each student, an array of n and unsigned integer to represent the ID, an array of strings for course ID, and so on and so forth. Okay? And the association between, so the relation between each name and each family name and each ID is due to the fact that position into the array is the same. So the ith name in the first array correspond to the ith family name in the second array and correspond to the ith ID on the third array, and so on and so forth. Okay, but I mean this kind of association, in some sense, is quite naive, because you have to deal with the association by your own. So you have to remember that the ith name is associated to the ith surname, and so on and so forward, and this relation is left to you. Okay. So we may want to define a more complex data structure, and to use this data structure as a type for the single cell of the array. So it would be nice to have the data type student, and to have an array of n student. Okay, and each student, so each cell in the array, should have a name, a family name, and an ID. So to do it, we can use the syntax struct. So in the C programming language, struct is a way to define a new data structure. So by writing struct structure name, open brackets, set of let's say properties of that structure, close brackets, we are able to define a new data type. Okay. Each of the properties I just mentioned are called members of the. But each of the property I just mentioned is called member of the data structure. So for instance, we are able, by using the struct syntax, to define the type course. And each course will have, of course, an ID and a mark. Okay. So how can we use then this new data type we have just defined by using the struct syntax? Well, we can use it just it was a standard data type. So just like integer, just like character, and so on and so forth. So the idea is that you can define variable of cost t. We have just defined the structure cost t. To declare variable of the type cost t, we have to write struct cost t and the name of the variable we want to deal with. You can define arrays of cost t. Again, this can be done in the usual way. To define an array of a given data type, you have to write the name of the data type, the name of the array, and in the middle of the square bracket, the number of cells in the array. And here we are doing exactly the same thing on the second line. So we are providing the name of the data type, which is struct course, the name of the array we are declaring, which is my courses, and the number of cells in the array, which is 34. Okay. Now, last things, of course, we may also have pointers for that new data type. So again, how can we declare a pointer to a given data type? Name of the data type, star, name of the pointer. And here we have exactly the same syntax. So if we want to define pointer to the new data type, we may write struct cost t pointer. And that's it. So quite easy, nothing special. Now, how can we access to the members, so to the value stored in each specific instance of the data type? Well, we can use the dot. So the idea is that, for instance, for each object, let's say, let me call object, is not a proper way to call this instance of this structure, because name object has a specific meaning in different language, while in the C programming language is not really, let's say, part of the language itself. So if I want to assign a new ID to an instance of the structure course T, I can do what is done in the first line. So in the first line we have a variable, computer programming, which has been defined to be of the type struct course. If you remember, the type struct course has a member name ID, which is an assigned integer. Okay? So to assign it, we can simply write computer programming dot ID equal 15. So I'm assigning a value 15 to the member ID of the instance of the struct course T, which is contained by the variable computer programming. Okay. Of course, the very same thing can be done also into the instance contained by an array. So if I have an array of courses of struct course T, of the type struct course T, I have many instances of course T values. Okay? So there would be an instance in the cell number 0, in position 0, there would be an instance, in the cell number 1, an instance, a different instance in the cell number 2, and so on and so forward. So we may want to deal with the instance in position 5. So if I want to change the value of one of the members of the instance in position 5, simply access to the instance in position 5 as we has done till now. So take the number of the array, square bracket, position of the instance you want to deal with, so position the cell you want to deal with, dot, and now name of the member. Okay? Is it clear? Please say something. Yes? What about you? More or less. Really? Don't be shy. Okay. What about you at home? So the second line is basically focusing on the instance of the course T in the cell whose address is 5, and then changing the grade member of that specific instance. Okay? Now, if you are, computer programming computer programming is a variable, and my courses is an array. So we have used the dot syntax simply because we were dealing with, a specific location. We are not dealing with a pointer to a specific location. If we have a pointer which points to a location in which we have an instance of the new data type, okay, to access it, we must use the star notation. So we must say, take the pointer, which is a pointer to an instance of the new data type. Look at that instance, and this is done by the star notation, as usually. And then to access the member, we may need to use the dot notation, okay? However, this is quite, from the syntactic point of view, is quite a difficult way to specify I want to access to that specific member. So the C programming language provides you a shortcut for this notation, which is the arrow notation. So the arrow notation means takes this pointer and look at the member in the instance of the object I want to deal with pointed by this pointer. Okay, so instead of writing asterisk pointer parentheses dot, you may write pointer arrows. Okay, as we did in the last line of our code. So in the last line of our code, we have a pointer pointed to an instance of the type struct cost e, and we want to change the grade member of that specific instance, and this is done by using the arrow notation. Okay, nothing really difficult. Now going back to the student example, we may define a new student in the way you can see on the slides. So a student is actually a specific instance of the struct student t data type. So each student will have a name, and here I must assume that 100 characters are enough to represent any possible name, first name for any possible student in my university, well, in any university actually. We will have a second member which is family name. Again, here we are assuming that 100 characters are enough to represent any possible surname. Any possible surname for any possible student. We will have an ID for my student, and we will have a member which is actually of a new data type. So while the other members of the struct student are standard data type, are instances of some standard data type, for the fourth member, we have a new data type defined itself by using the struct syntax. Okay? So the new data type defined by using the struct syntax can be themselves used as types for the members of the data type. Okay? Now, using the struct word is, well, using the struct syntax is nice, but I mean, it's not that nice if you are writing code. So having to write struct at the beginning of, just before the name of new data type you have defined is not really fine, let's say. You're wasting a lot of time writing struct, so on and so forth. So we have a way to add the new data type to the list of types, let's say, embedded in C, and this can be done by using the reserved word typedef. So by using typedef, you are basically saying, look, I'm defining a new type which is not a struct. Okay? Well, which may be or may not be the struct. And from that point on, you can avoid to write struct, basically. So in the first line here, I'm saying, look, what I define as struct cost t from now on will be called course underscore type. And from that point on, I can use it as course underscore. Actually, is an alias for the int type. Okay, so typedef can be used both for struct defined data type and the standard one. So, but actually they are not really the same. So using the struct word has some advantage with respect to the data type embedded into the list of types by using typedefs. In particular, if you have a look to this code, you understand that by using the struct word, we are able to define functions which has the very same name of some structs. So if I have the struct cost t, I can define the function cost t, but this doesn't hold for the types included in the list of types of the program we are writing. So by defining the type cos t by using the type def reserved word, I'm not able anymore to define the word, the function cos type. So, I mean, using the reserved word struct may be useful from that. And oh, this is a quite important thing to say, and then we will end the lesson. Let me think. Not really. We will have a demo. So as I told you, there may be situation in which you include twice. You try to include twice the same header, and because of cyclic definition, basically. Well, as I told you, it's not possible. As I already told you, or at least mentioned it, it's not possible to define twice the same structure. So if your structure is defined into an header, and the header is included twice on the same source, you may end up in seeing twice the same definition for the same data structure. Okay, and this ends up in an error. The compiler is telling you you are trying to define twice the same struct, which is not possible. So how can we handle it? And we already mentioned the solution. The solution is to use the preprocessor. So if in each header, before defining anything, before defining the signature of the function, before defining new struct, you check whether the header has been already read by the compiler. And if this is not the case, you define a new macro, and then you do everything you want. Then you end up in avoiding double inclusion of the same header, or better, you end up in avoiding double definition of the same structure. Okay. And this is it. Now let's try to have a demo of what I've said till now. Let me see. Oh. This is it. So let me define. Let's see. This is our main file. Okay. Yeah. Still there? Yes. Okay. So here we may define the main function int argc char argb. Oh, by the way, I use these two names for the formal parameter, but it's not really necessary. I may change it, of course, I don't know. Let me change it in D and C, for instance. It's not really, they are not really evocative, but this is just to show you that everything works exactly in the same way, even if I change that names. Turn 0. Now, let me declare a variable n, and I want to do the following thing. If c is smaller than 2, return 1 and print f error. Okay, so if the number of parameters at the command line are less than 1, then I print f error on the standard output and I return with a value different from 0. Please notice that this value c is the number of parameters plus the name of the executable at the command line. So that's why here I'm writing 2 instead of 1. Now, if this is not the case, I want to, as we already did on the slides, I want to, let's say, read from the second parameter, which is provided by v1. I want to read a decimal number, and I want to place it into n. Okay? And once this is done, I want to print f. Let me see. Success. Okay, so quite easy, nothing special. So here I'm testing whether there is at least one parameter at command line, and here I'm reading, let me write in this one, reading an integer number, the number from the first parameter command line. Now let me close it. Let me try to compile it. Oh, we have here we are getting an error. I wrote ss_scan, but it is ss_scanf. Well, ss_scanf. So let me again going back to my code, and the error was here. Again, let me try to compile it. Everything went as expected. Let me try to execute it. Error. Why? Because the number of parameters passed at the execution time at command line is less than 1. Now let's try to pass, for instance, 1 parameter. Let me use the number, I don't know, Donald Duck plate car, and this is it. Okay, what if I try to, let me reset, what if I try to do something like this? Why? Well, we got a strange result. Why? Well, the point is that everything in our computer is represented as a sequence of bits. Okay? And so, what is represented as RS is actually maybe interpreted as a number actually. Okay. Great. So now let's move on and try to see whether we can probably, but well, I don't want to show you anything nasty. So this is our program. Now let's try to write the function which is able to compute the first and prime number. So unsigned int pointer get primes signed. So our function will take a natural number and will return a pointer to a memory location which will be used to store an array of n numbers. So first thing to do is to declare a variable which will be used to store the position of the array we want to deal with, which is unsigned. To do it, we write unsigned star p, well, unsigned star p, let's do it this way. Okay, this is the pointer to the prime we will compute, return p, and we will return that pointer at the end of the computation. Now, let me allocate the space for the array we want to deal with, and to do it we can use calloc, for instance, or malloc, as you prefer. Well, I rather prefer malloc because it basically does not initialize our array, so it's not wasting space for something that we will going to initialize by our own. And to do it, let me use my syntax. Sign. So here we are typecasting the result of malloc. We need n cell in our array, and each cell in our array size takes a number of bytes, which is the size of unsigned. Okay, so now P is a pointer to memory location which is able to store up to n number. Now, so at this point this is done. So now let me declare another variable, which is the variable of the already compute. Okay, so let me call it already or better computed. So this variable will tell me how many primes number I have already computed. At the beginning of computation, of course, will be 0. And what I need also, I need another number which is, let me call another variable called d, because n is already gone, so let me call it num, which is the variable storing the number which will be tested to see whether it is a prime number or not. And let me start from 2, since we already know that 0 and 1 are not prime numbers. Now, while computed is more than n, what we can do? Well, we can test whether num is a prime number. So how can we test whether num is a prime number? Well, we can exploit the already computed prime number, for instance, by using I don't know how to call it, Crivello. Well, it's a method by Eratosthenes, and the idea is to see whether the already computed prime number can divide the number you are considering right now. If this is not the case, then your number is a prime number. You don't need to test all the possible numbers, but you may focus on the prime numbers themselves. So let me define another variable, unsigned int j, for instance, and this j will go through all the elements in the array P which has been already computed. So we'll go through all the possible prime numbers which are smaller than the value num. Okay. So while j is smaller than computed, and number, this is the modulus of the division, so the number divided by pj is different from 0. Right. So j will go through all the possible already computed prime numbers, so of course it should be smaller than the computed prime number. And if the number I'm considering divided by that prime number is different from 0, I can go on, otherwise I discover that the number is not a prime number. And what? And okay, let me leave it here. I mean, we can tune it later on, but this is more than enough for the moment. So if this is the case, I can increase j by 1. Okay? So I keep testing everything until I end up either in a situation in which the number I'm considering is can be divided by pj, or j is equal to computed. So if j is equal to computed, then the second condition does not hold, and then for sure num is a prime number, so I can p computed, assign to p computed the value num, and increase computed by 1. Well, in both the cases, so if this condition, so if j is equal to computed, or if either j is equal to computed or is not equal to computed, so in both the cases, for sure I must increase num by 1, and this is it. This seems to be everything I need to do. Yes. Now, let's try to use that function inside our function, main function. How can we do it? So let's go back to our function. And so now the first parameter has been saved and interpreted as a natural number by using this scanf. Here we are printing success and the number. And let's try to use our getPrime function. To do it, first of all, we need to declare a variable which will store the pointer to our primes number, and then we need to call our function. Oh, you are missing the code probably. Let me try to. Okay, that's much better. Okay, so now we need to call the function getPrimes, and to call it, we will call it by using the value stored in n, which is the natural number interpretation of the first parameter in our program call, in our command line. And since we know that getPrime reserves some space for the primes number, we also need to remember that a free is required here. Sorry. Now, some of you may ask, what if I forgot to use a free here? Well, as soon as you exit from your program, everything allocated will be free by default. But I mean, if your program is meant to run for, let's say, one years, it's really important to remember to free unused space. Otherwise, you keep reserving space, and you never free it, and eventually you will end up in allocating all the free space in your system. You run out of memory, okay? So in this specific space, it's not really necessary because the program will end immediately. But I mean, from a formal point of view, it's much better to free the space also in this case, okay? Much more clean, and so that's why I'm doing it. Now, after the call, we know that the pointer primes refer to a memory space which contain an array of primes number. So let me print them. And here again, let me use unsigned. I mean, it's not really necessary, but I rather prefer to be, syntactically correct. So by using this for loop, I'm going to go through all the primes number we have just computed, and I can use printf. But let me write printf here. So here I'm going to write ith prime to column and the number I've just computed, and this is done by remembering that I can use the array syntax for even for pointers. So if I want to access to the ith element pointed by primes, I can simply write primes square bracket, as in this case I, and this is it. Okay, so let me try to compile this piece of code. Oh, by the way, I never said it, but GCC has a parameter called minus wall. That means bring me all the warnings. So capital W means warnings, and all means all. Okay, and this basically put the compiler and the preprocessor and the linker in a very scrupulous modality, and this modality tell you any possible problem. So it is in some sense even too much scrupulous from a certain point of view, but I rather prefer to be sure that everything seems at least to be fine. Now, if I try to execute this piece of code, we already compiled it, everything seems to be fine. So let's try to, 300 probably is too much. Let me see, 30 for instance. And this is it. Oh, here we have a bug actually. And the bug is due to the fact that here we may have not the ith number, but the ith plus 1 number, because the first one is the 0th, which is wrong both from the English point of view and the starting point of view. However, we were able to compute the first 30 prime number in a really easy way. Let me go back to the command line. Here, as you can see, we are taking the first parameter as we are using the first parameter in the command line as parameter for our function. We transform it from a string to a natural number, and then we are passing as first parameter in the get primes function. The result is stored in a memory location dynamically allocated, and that's it. Any question? Are you still there, you at home? I hope so. So let me go back to the code just to answer your previous question. So the question of one of your colleagues. Here I'm using this malloc, and I'm using this typecast. Let's try to see what's going on if I remove this typecast, and I call malloc and assign the result of malloc to an unsigned int pointer p. Let me see. Again, here I'm calling the compiler with minus wall option, and I'm not getting an error. But let me slightly change the code again, and let's try to see what's going on if I change it in this way, for instance. Okay. So the original code was this one, and I showed you that the typecast in some sense not necessary. Now let me slightly change the code so to show you that could be useful. So let's assume that for some reason I decide to allocate some space, and I'm thinking to reserve this space for a floating point number, for floating point numbers. Okay, and let's try to see what if I try to compile it. Here I'm getting an error. So that's why I rather prefer to use the typecast rather. I prefer to use the typecast rather than not, because in writing my malloc, I was thinking to use this space for storing floating point, and that's why I use the typecast to floating point. But since I'm assigning this space to a variable which is not meant to store a pointer to floating point, I'm getting a warning. Okay, so by using the typecast, I discovered an error in my code, which weren't how can I say, weren't emphasized by the compiler when I was not using the typecast. So my suggestion is every time you invoke, you call calloc, malloc, and so on, please use the typecast, because give you the chance to check whether you are really doing what you think you are doing. Okay. This is it. Any question? I mean, this. This function can be implemented in a much easier way by using a function to detect whether a number is a prime. So if I have a function to detect whether a number is a prime, I simply have to test whether num is a prime number, and if this is the case, I use this block of code, otherwise not. And if I want to, this is not the best implementation also for getting a prime number, because for instance, I can end up the computation when I reach prime number which is greater than the square root of num, for instance. But however, this is still more than enough for what we want to pinpoint. Do you have any special request? Okay, so let me try to write the prime numbers into a file. Okay? So let me write file output equal fopen and the file how can we call it? Well, let me slightly change the code here. Instead of 2 parameters, I will take 3 parameters, and the second parameter will be used as output of our for our computations, and so v2. And we will use it as in write mode. You are missing the code. Sorry. Okay. So by issuing this instruction, by using this instruction, we are opening a file whose name is the second parameter given at the command line, and we are opening it in write mode. And the descriptor of this file is assigned to the variable output. Now, sooner or later, this file should be closed. Again, as soon as you end the execution of your program, or the file descriptor will be closed by default, but I rather prefer to close by myself. And how can I write my files? Well, I can use, for instance, the fprintf function, which takes as first parameter the file descriptor, in this case, output. Let me save it. So I simply added two lines, the first one to open the file, the second one to close the file, and in the middle I slightly change the fprintf call, the printf call, meaning I put an f in front of the printf call, and I said, and I pass as first parameter in the call the file descriptor I want to write. Now let me compile it again, luckily no errors, and let me execute it. If I try to execute this stuff, I get an error, and this is expected because I changed the check at the beginning of the execution, so we need at least two parameters. The second parameter can be, I don't know, let me say 3, for instance. It would be a mess, but we will use it. On the output, we have on the standard output we exclusively have success 13, which is 30, which is expected. Let me have a look at the current directory. We have a new file called whose name is 3. Oh, let me do it this way. A new file whose name is 3. Let me look at the head of this file by using the command head. Let me reset the stuff at 3, and this is it. So again, writing data into files is quite easy. We could get almost the same result by using redirect, of course. Okay, so if we left the code as it was by issuing the command a.out30, and then by using greater than 3, we end up in a situation in which the first line will be success 13 and the remaining line will be exactly the same. And this is it. And okay, let me again do the last thing. So I would write the number 13 into a file name. How can it be? Primes configuration. Okay. So here I'm writing the number 30 into a file name prime configuration. And I want to change again my code for the very last time. Let me go back to the previous situation. Here is 2. And I don't want to read the well, no, this is okay. I don't want to read the integer number from the first parameter, but I want to read it from the file primes config. How can we do it? Again, to deal with a file, we have a variable. We need a variable. I mean, here I declare already a variable output, which is of the type pointer to file. I may use a very same variable actually, but I want to distinguish it because it's much clearer. Using a variable output to read a configuration file is not the best way to write your program. So let me change the variable. So configuration f open. Here I want to read the file primes configuration, and the modality will be read modality. So I don't want to overwrite the file, I want to read it, and of course at some point we will need to close that file. Let me do it. This is it, and here we need to change this scanf instruction. Go a little bit up, and to change how can we change it? Well, we can replace the scanf function with a fscanf function, and the first parameter will not be an array, but should be a file. So this instruction is now reading a decimal number from the configuration. And we also need to change, of course, this instruction, because here we are reading the output, the name of the output file from the second parameter. I mean, let me read it from the first parameter. I think this is more or less everything. Okay, so let me delete 3 just to show you that everything works as expected, as it is expected. Let me compile again my main file. Everything seems to work properly. Now, so the first parameter, in the last version of our code, the first parameter will be the output file. So let me call it output.txt. Now, as you can see, I'm not reporting any values in the command line, but my program is able to read the number 30 from the file primes.config. And so if I have a look at the tail of output, I end up noticing that I was able to compute exactly 30 numbers. What if I change my prime config? Instead of 30, I want, I don't know, let me see, 40. Okay, so now, right now, my primes configuration file has the number 40 written in it. And again, if I invoke my program, so if I execute my program by issuing exactly the same command, you see, by changing my configuration file, I was able to change the result of my execution, and actually the final lines of my output are consistent with what I expected by my execution, by the computation. Now you may wonder how many lines contain my output. So I can use the command word count to count the number of lines in a file, and this can be done by issuing word command -L, saying you have to count the number of lines, and passing as parameter the name of my file, and we see that we have 40 lines on the output, which is exactly what we expected. So how can we? So let's assume we are trying to build up a system which remember all the computation performed by our program. So instead of deleting the output file, is keep updating it, but by attaching the result at the end. How can we do it? Well, let's go to our source code. Let's go to the instruction which deals with opening the file, the output file. Instead of writing W, we may write A, which stands for append. And let me see. Everything seems to work as expected. So let me count the number of lines in the output. Now let me again executing my instruction. Everything, executing my executable. Everything seems to work exactly as before, but if I have a look at the content of my output file, now I discover that instead of replacing the previous result, by changing that modality, I was able to attach the results at the end of the file. So I opened the file output.txt, but I not deleted. I didn't delete the content of the file itself, but I simply attached the new result at the end of the file. Okay? Okay. Get this error. Prova C error object unseen int is not a function proper. Unsigned int is not a function or a pointer assigned int. Yeah. So I'm seeing that some of you is getting an error. Can you send me your code by mail so I can understand what's going on? Because just by looking the error, I'm not able to understand what's going on. Just to try, have a look at the previous at the function. Have a look at the instruction at line 6 and check whether you have a semicolon at the end of the instruction. Okay. That's it. So if you don't have any further question, that's all. You will find so this is the demo code. On Moodle you will find some further material about what we saw yesterday and today. So please have a look at it and try to exercise by your own concerning this stuff. So try to, I don't know, figure out a function to get the first 2000 odd numbers or whatever you want. Okay? You have to try. And that's the best suggestion I can give you to really understand what's going on here. Because you can see me coding for 1,000 years and you still don't know what's going on otherwise. Okay? Then, see you tomorrow and enjoy the night. Yeah. You have a problem. I have many too.
No, the most recent one is that my program stops at success and number. It doesn't get the prime numbers
At all.
yes.
Okay, so in this case, I encourage you to send me your code
Okay.
and tell him. And so, okay, so try by your own. But if you get stuck in some error, please send me an email with your code attached, and I will try to answer to all your mails as soon as it is possible, and replying by saying, have a look at that line, here we have this problem, and so on and so forth. Okay? Okay, thank you, and see you tomorrow then. Bye.